Here is the introduction to the gas laws. And so it's basically what we just went over in the previous lecture, but they actually name these. Now, for our class, I'm not going to require you to know the names of these. I mean, become familiar with them, but there's some memorization you have to do, but I'm not really big into memorizing things, really. I'm more into understanding things. You know, can you look at a problem and know what to do? Maybe you don't know the name of the law that you use, but you can figure it out. And not only figure it out, you understand what you're doing, which is way more important, I think. Okay? But I do want to show you this. The gas laws have 4 basic properties. You know, we looked at pressure, volume, temperature, and moles. This is like the molecules, just like we talked about in the previous one. And the gas laws describe the effects of these. So we kind of already went over this, but let me just show you that there's actual laws. Okay. Volume and pressure. Volume is indirectly proportional to pressure. Okay? So here's my little animation here. You see as volume goes down, pressure goes up. Okay? And that's just what we talked about. Let me see. Remember we had the containers. You're going to have to bear with me drawing these again. You know, I have a large container. Okay? And a little bitty baby one. Okay? And I put my gas molecules. Oh, it's almost the same color. Let's do that one. Okay, you can even see that. Let's do brown. And of course, this is almost the same color too. Okay, and I put my gas molecules in here. Do you see, remember, that pressure is when you hit the container. Okay? That we have a greater chance of these gas molecules hitting the container because the container is so small versus this one. They have so much room to go, so it's going to take a much longer time. So as your volume decreases, so it gets smaller, your pressure increases because it has a higher chance of hitting the container because it's so small. Okay, think about yourself in here. Let's say, I don't know, you're in a 1,000 square foot room, okay, a really big room. And now put you in a 10 square foot room, okay? Are you going to hit the wall sooner whenever you're in a 10 square foot room or a 1,000 square foot room? Well, the answer is 10 foot because it's so small you barely can go anywhere. Okay, and this law has a name. It's called Boyle's Law, okay? And here's the formula if you want for Boyle's Law. Volume is 1 over pressure. But I'm going to show you how to derive each of these so you don't have to memorize them. But if you want to know, Boyle's Law is 1 over pressure, meaning volume, as volume goes up, pressure goes down. You see pressure's on the bottom. Here's Boyle's Law. It says P1V1 equals to P2V2. And this is just again comparing 2 sets of pressure volumes. And this is just, I don't know, initial and final pressures. So it's kind of like your dilution we did. So if you have a pressure 1 and a volume 1, you can calculate your pressure 2 and volume 2. Okay, and that one's called Boyle's Law. I guess we can look at this example here. Actually, no, let's not look, because we're going to get to PV equals nRT, and I'm going to show you how you don't have to memorize all of these. Okay, but just know, Boyle's Law compares pressure volume. So same, I mean, this is Boyle's Law, comparing pressure and volume. And this is when we're looking at 2 sets of data. There's Charles' Law. Charles' Law looks at volume and temperature. So what do we say about volume and temperature? Okay, or as the temperature increases, pressure increases, right? Okay. Volume is directly proportional to temperature. As something gets hotter, it expands. Okay, so this is looking at volume. So as something gets hotter, it expands, okay? Think about boiling water. So first it's in that container. When you boil it, it becomes a gas, and then it expands into the whole entire room, okay? So if something gets hotter, it expands. Also think about kind of like melting or something, you know, like a metal. We have a metal in a cube, and then you boil it, get it hotter, and it's going to expand out. And then Avogadro, where Avogadro's number is the same person. So this, of course, has to do with the amount, okay? So moles. So as, let's see, volume and number of moles are proportional to each other. Okay, think about blowing up a balloon. As you put more air in there, it expands, right? So it just basically says, you put more into the container and it will expand, okay, like a balloon. So as you put more molecules in there, the volume will expand. Okay, and that's all that says. And then here is the ideal gas law. This is when we put everything together. Now let me show you how you could derive everything from this. Okay, so let's get out of here and let's do the ideal gas law, because that's really only one you need to know. Let's use a prettier color here. Okay, so we have PV equals nRT, right? Okay, so all of these we're usually looking at two sets of data, okay? R is a constant, just R is there just to make the units cancel out, okay? So we have, if we bring everything over, PV, and let's make it equal to R. Okay, so we're going to bring N divided by and T divided by, so PV equals NT. So all I did is I brought the N over and the T over, and now they're divided by, so PV equals NT, which equals to R. And let's say these are your initial, okay, your initial conditions. Now, so let's say conditions 1. Now we're going to look at conditions 2, so your final conditions. So PV equals nRT. So you calculate it again, and let's set these equal to R. So again, we'll have PV equals NT equals to R. But these are your second conditions, okay? But do you see how both of these are equal to R? This is the same R, okay? Alright? So R is a constant, meaning it doesn't change. It doesn't matter what gas you're looking at, R is the same. It's just there to cancel out units, because if I bring it down here, pressure, let's say, is in, I don't know, atmospheres, volume in liters, N is in moles, and then T is in Kelvin, okay? Now we're saying that this side equals to that side. But do you see the units don't cancel out at all? So how are they equal to each other? Well, that's where R comes in, and R has all of these units in it. It has, like atmospheres, liters, moles, which one? Oh, and Kelvin. Depending on what your units are. It has all of those in there so you can cancel out your unit. So it's just there to cancel out your unit, and it never changes, okay? Just depends on your units. So let's look at this. Now we have, if we set these equal to each other because they both equal to R, we have P1 V1 equals to N1 T1, which equals to P2 V2 N2 T2. Okay? Now this is like the formula I would memorize. This one here. I wouldn't memorize all the other ones because they are basically this formula. Okay, so let me show you. Let's look at Boyle's law. Remember, that was pressure and volume. So all you do, so let's say in your problem, it only has pressure and volume in there, okay? It only talks about pressure and volume. It doesn't say anything about moles or temperature. But watch this. I cancel out moles and temperature only because it doesn't talk about them, okay? And what did I just derive here? P1 V1 equals to P2 V2, which is Boyle's law. Okay, let me show you another one. Let's do this problem right here, okay? So we have 465 liters of helium gas. Hold on, let's do this one here. Wait, that's the one we just had. Let's use this one. Okay, a sample gas has a volume of 2.8 liters at an unknown temperature. So we're trying to find this temperature. When the sample submerged in ice water at T equals 0, its volume decreases to 2.57. What is its initial temperature? Okay, so we have, let's look at the problem. Sorry. We have, you see liters and temperature in there. That's the only thing that it talks about. It doesn't talk about anything else. So we have our initial formula here. P1, V1, T1, and 1. P2, V2, T2, and 2. Okay, so what was it? We have only temperature and volume in liters. So let's erase everything else. So it didn't talk anything about pressure, nothing about moles. It had a volume and temperature, no pressure, no moles. So what do we have left over? V1, T1 equals to V2, T2, okay? That's because that's the only thing it talked about in the formula, or in the problem, so I don't need anything else. And let me actually go back. So this says Charles' law, and let's look at Charles' law, let's see what it is. Look, V1, T1 equals V2, T2, which is exactly what we have right here. So we derived Charles' law without even realizing it. Okay, now let's put in our, what we know. So initially has 2.8 liters, okay, so we'll say volume 1 is 2.8 liters, okay. We don't know the temperature one, no, we don't know that, that's what we're trying to solve for. And let's look at everything else. When the sample is submerged in ice water at T degrees Celsius, okay, so we don't know, T2 is 0 degrees Celsius, and the volume is 2.57 liters. Okay, so volume 2, 2.57 liters. Okay, now we usually put this in Kelvin. So remember, degrees Kelvin, or this is just Celsius plus 273 is degrees Kelvin, so 273 Kelvin. Okay, that's just a little conversion. Okay, so now let's put everything in here. So our volume 1 is 2.8. We don't know our T1. Our volume 2 is 2.57. And our T2 I'm going to put in as 273. Okay, so we're gonna, let's do 2.57 divided by 273. So 2.57 divided by 273. Okay, this equals to 0.009. So we have 2.8 over T1 equals to 0.009. Okay, now let's bring T1 over. So 2.8 equals to 0.009 T. Now we bring this over and divide. So 2.8 divided by 0.009. So your temperature I have is 1.04. That sounds weird. Let me make sure I put this in right, just to make sure. Oh, okay, yeah, I did something wrong there. So this should be 297. Let me see what I did here. So I did 2.57 divided by 273. I might have put my decimal in the wrong place, but I said 2.57 divided by 273, 009, and then so I got 2.8 Oh, it's because this needed to bring, oh, I multiplied there. Okay, so then 2.8 divided by 0.009, okay, which is, this should be 311. So let me show you what I did. Doop, 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 doop. Okay, so okay. I bring this over, so let's bring let's go the opposite way. I bring the 0.009 over, it's multiplied here, or it's just there, so we divide over here. So we'd have 2.8 divided by 0.009. This is 311, so we'd have over T1. Okay, and then you have to bring this over. There we go. Anyway, so this, what did we get again? No, I can't remember. 2.57 or 273 multiplied by 2.8 divided by 2.57. Okay, about 300. Okay. Anyway, so that's how you do the problem. You literally just put your numbers in, you solve for your unknown, and you're done. And this is the formula you need to use. P1, V1, T1, N1, P2, V2, T2, N2. Okay? And again, this one should be 97 Kelvin. Okay? And let's look at what we calculated too. So 297 Kelvin. So whenever you do this here, so temperature, volume, so we started at 297 and it went to 273. So do you see that it got colder? So temperature 1 is 297 and it went to 273, so it got colder. And do you see that this got smaller? Remember, the volume expands as the temperature gets higher. Okay, so hopefully that gives you an introduction, and in the next one, the Khan Academy will go over a little bit more into PV equals nRT and go over a lot of examples with you.